another video. This week my old CRT TV broke down. It worked for about 25 years more or less, which is about 20 years more than you can expect from any modern piece of electronics. But it wasn't worth fixing, so I just decided to salvage some nice parts out of it. This flyback transformer and a bunch of coils and caps and nice bits and pieces. I watched some YouTube videos on how to set up the flyback transformer, but what I saw is that most of them just focus on how to get the transformer to work and produce these nice sparks that you see here. So I thought this would be a good opportunity to make a video, not only showing how to connect the flyback transformer specifically, but how coils work in general and how we use them in different applications. So here we go. We're gonna start by having a look here on the board. I have a whole bunch of different coils, which some of them I took out of the TV, like these big ones, and other ones I just had. But they all work on the same principle, and that is we have an insulated copper wire that is wrapped around a metal core. The core doesn't have to be metal. We're going to talk about this in a bit, but they all work on the same principle. Again, just a wire wrapped around the core, and we're going to discuss the different ways that you work with the coils and the properties and what they do, just in layman terms, so that it will be easy for you to understand how eventually I got the flyback transformer connected, just like you saw at the beginning of the video. So we're going to start with the very basic, just a little bit of theory. I'm going to set here everything aside for a moment, and let's have a look at this little drawing that I've made here, just to explain the theory first. What you see here in the middle, this is the Earth. And the Earth is spinning in space, and it's producing these magnetic fields. It produces the magnetic fields, to put it in a few words, because it has a molten metal core that is rotating around the Earth. It's churning inside, and around it there is a whole bunch of insulated conductive material, like there is rocks and sand. And in between them there is iron and water and conductive materials, and those spin around the molten metal core, and it produces these magnetic fields. Now one thing that you need to understand about this phenomena is that if for example we would take a very long wire, and here I have a little space shuttle or airplane, what I tried to draw here. And if we take a long wire and we connect one end to it here, and we will just drag it all across the magnetic field, the wire would get charged up with millions of volts of electricity, which is inducted through from the magnetic field. So the magnetic field would charge the wire simply by the friction that it goes across it. Now, you don't need to understand this too much, but it will help to understand other things that I'm going to explain here in this video. So keep this in mind. And we're going to look at the first, most basic example of a coil, which consists of a solid iron core and a piece of insulated copper wire. Some people call this magnetic wire, but it's just enamel coated wire, just a wire with a clear coating on it, so that there won't be any conductivity between the layers when you're winding it up. So what I'm going to do is I'm going to wind this wire around this metal core. Once I've coiled the wire around the metal core, I take a small piece of sanding paper, and I just expose the ends, so removing the coating around the end of the wire so that I can make a connection. And I'm gonna connect the coil, just set it up on a breadboard, and I'm going to connect it to a battery now. So this is something that you shouldn't be trying yourself, because this is a really small, a short coil. So the wire here is just about 2 meters long, and that will basically short out the battery. But just momentarily, I'm going to show you the effects of the magnetic field being produced by connecting the negative, the positive to one end of the coil and the negative to another end of the coil. And we can see that we have a magnetic field. So here we have a small washer, and the washer basically sticks, and I can feel the battery already warming up. So this is the magnetic field. Once I release the battery, the field collapses, and we have no more, and the magnetic field is gone, so the metal will no longer stick to the core itself. Another thing that I'm going to do now is I'm just going to take this out for a moment, and I'm going to make a measurement of the resistance in the coil. And I need to set my my cheap multimeter here on the lowest resistance value, so it just checks for shorts. And I'm going to connect one end of the coil and another end of the coil, and we have a short, but we can also see that we have a resistance of 1.8 ohms in this coil. So I'm going to note this down for a moment, just so that we can look at this value in a moment. So I'm going to write here 1.8 ohms for the small coil and set this aside. The next thing that I'm going to do is I'm going to create a bigger coil. So I'm going to take again the same idea. I'm going to take a metal core, and I'm going to wrap around it a copper wire and produce this coil here, which is bigger than this one. This one has about 2 meters of insulated copper wire, where this one has about 10 meters of insulated copper wire. And the same idea, I'm going to connect it. I'm not going to connect it to a battery, because we already saw that, but I'm going to measure the resistance in this coil. So again, taking my multimeter, connecting one end of the coil and then the other end as well. And again, we have a short, but this time we can see that this coil has a resistance of 2.5 ohms. So it has more windings on it. It has about 10 meters of wire on it. The previous one had about 2 meters. So I'm going to note this down. The second coil, this was our first one, and our second one is 2.5 ohms. This explanation just dealt with the magnetic field being produced in the coil, and you saw how it's being magnetized. But another thing that you need to know about coils is that once we release the current, the magnetic field will collapse, and it will push electricity. It will push all the electrons that are built up in the magnetic field through the coil, and that will produce a voltage spike. So to see this, I have here just a small breadboard, and I'm going to connect my smaller coil, basically just receiving a positive, and here I have a button and the switch, the switch is off. It's a momentary on switch, so when I press it, I'm connecting the coil to ground. But when this button is not pressed, then the coil will just take the electricity and go through this diode and then back to ground through this transistor. But what we're going to look at in this example is the collapse of the electromagnetic field and the result that it is giving. So I'm going to connect my multimeter. One end I'm going to connect to the ground, and the other end I'm going to connect to this behind the diode. We're going to set it on 20 volts, that is good. And I'm going to take now my battery and just give it a positive and a negative. So right now I have my homemade coil here connected. I have the battery. You can see that the battery provides 7.34 volts. But right now the circuit is complete. So the coil it takes it receives the voltage and it just passes it through this capacitor to ground. Once I press this button, I'm going to create a shorter route to ground, and that means that the electricity will flow from the coil instead of through this diode and the capacitor. It will flow directly to the ground. Once I release the button, the magnetic field will collapse and it will produce a voltage spike, and we're going to see this voltage spike on the multimeter. So right now it just again it takes the electricity and it goes through this capacitor. Once I press this button once, you can see that we had a small voltage spike there. If I do it a couple of more times, then you can see how we went from 7.3 to 9 point something. And if I keep on doing this, then you can see now we are producing 10 volts, and the faster that I press this button, the higher it will go. Obviously, also depending on the coil itself, the size of the coil and the voltage and the current that we're providing it. So what I'm going to do next is I'm going to take a bigger coil that I made and connect it here, and we're going to see the difference between what the spike from this smaller coil and the larger coil. So first of all, let's just see again. Here we are producing about 10 volts every time that I release the button. So I'm going to connect this larger coil and we're going to see the difference. I've connected the larger coil that I've made. Again, this one has about 2 meters of insulated wire wrapped around it, and this one has about 10 meters of wire wrapped around it. Once again, right now, I'm not providing a shorter route to ground, so the circuit produces 7.24 volts. Once I do it again, I'm going to press this button, create a shorter route to ground, and then release it so that the magnetic field collapses, and we're going to notice the change in the voltage spike between this small coil and this larger one. So here we go. Just pressing this button immediately gives out an error because the voltage is probably too high in this case. So I'm going to move it from 20 to 200, and when I do this, we are producing a voltage spike of about 30 volts, as you can see here. I'm going to do it again. And this is the result of the magnetic field collapsing in the coil and pushing all the electrons out of it, providing more voltage than what we've actually supplied this circuit with. So the next step is to have a look at what happens when I add another coil on the one that I already made, so that we will have two coils wrapped around the same core. And I'm going to do this by taking again my smaller coil, and this time I'm going to take a shorter piece of wire, which is about 50 centimeters long and I'm going to wrap it around it. And we're going to talk about the next phenomena, just like I discussed at the beginning. If we were to take a piece of wire and drag it across the magnetic fields of the Earth, that wire would charge up with millions of volts. So we're going to reproduce this only in really small scale. So I'm going to wind this secondary coil, and I'll be right back. Okay, so I've wounded another coil around the one that I already made, and right now I'm using the shorter coil, the one with the 50 centimeter piece of wire, as a primary coil, and the secondary is the initial one that I've made, and I'm going to measure the voltage across the secondary coil. And I'm going to use the primary coil to do the exact same thing that I did previously. So we're creating a connection to ground using this button, then we release it, there is a voltage spike. But we're going to again measure the secondary coil. So not the one that actually receives the voltage from the battery, but the one that is connected on the same core. Right here you can see that we have right now 0 voltage coming out of the secondary coil. So I'm going to press this button, and you saw that we had a 0.2 millivolts of voltage coming across the secondary one. If I keep on doing this, then you see that what happens here is that we can charge, when we have two coils on the same core, if we charge one coil and then the magnetic field will collapse, some of the electrons from the magnetic field will go into the second coil that is wounded around it, and the more windings there are, the higher the voltage that it will produce. Also, obviously, the more voltage and current that you can give it from the power source, but the more windings that we have, the higher the voltage that it will produce. So to explain this now, since when producing your own coils, you're limited. You're limited by the amounts of windings that you can make and the precision of the coil and everything like that. So I'm going to move on to another example, which is this one. And here what I did, I just used a ready-made coil. So you can see here we have the core, and inside here there is the coil wrapped around it. It has a thinner wire than what I'm using to make the coil, but there are more windings of it. So right now you saw that we have the primary and the secondary, and when I press this button, then we're producing something like 0.2 millivolts. I'm going to set this circuit up in the exact same way as here, and we're going to see the difference. So here I've connected the second circuit that I just showed you. It works exactly the same, just like the first circuit. I used here just a ready-made coil as a secondary, which has much more windings, a thinner wire, but much more windings, and as a primary, just the one that I took a piece of wire and wrapped it around the core here. And nothing, no components here, just a button that allows us to break the circuit between the battery and the primary coil. So let's, if you remember, previously we produced about 0.2 milliamps. So right now I'm going to do the same. And we can see that we are producing already 4.2 or in that region. So we have much more windings here, so that means that we are inducting the voltage from the magnetic field produced in the primary to the secondary, because we have more windings, we can basically create more voltage output out of it. The next thing that I'm going to do is I'm going to simply scale this whole thing up. So instead of using this small coil as a secondary and this smaller windings as a primary that I've made, I'm going to take this this flyback transformer and I'm going to just reproduce the same thing, and we're going to see what happens with it. Okay, so I got the flyback transformer set up here, exactly the same like the previous circuit that you saw, the smaller one, which is this one. And it's again the same principle. Here you can see we have the ferrite core of the coil, and inside the transformer there is the same idea like here, a whole bunch of wire, only maybe 100 times or 1,000 times more than what this coil has. Here we have our primary that again I wound it around it, just like I did here. The only difference is that while here we've produced 0.2 millivolts, this one will produce much more. I'm no longer using a battery, and I can no longer give you measurements of this of the voltage that is produced here. That's why I used that's why I did the previous example. But I'm using a 12-volt power supply, which is which has a 1 amp, which can draw 1 amp. And again, here I have my button. When I press the button, you don't see anything happening because the rate is not fast enough. If you were to build this yourself and just put the two electrodes, the positive and the negative from the coil, from the high voltage coil, so the coil that has the most wrappings inside here, and you would press the button, you would see a very small spark just jumping every time from from the positive to the negative. If you touch it, then you can actually feel the charge, and it feels even better if you have the power on, but you can actually feel it. If you hold the button, nothing happens because again we're not the field is not collapsing in the primary coil. It doesn't produce any high voltages in the secondary, but once we release it and we press it again, then we get a small shock out of it. So this is the whole idea. This flyback transformer, it's a coil, but it's a coil that it's a bunch of coils that is already made into a product. So it has a few more components inside. In this case of a TV, it also has these pots here that you can adjust the focus on the TV, and it also has some diodes. Here at the back, you can see that we have a whole bunch of pins. Let me just take this whole setup off. So we have a whole bunch of pins here, and each two or more of the pins will be connected to one end of the coil. And if you want to find out which pins are connected where, just like you saw at the beginning of this video where I measured the different resistances of the smaller coil and then the slightly larger one, which I have here, you can see that the more wrappings, the higher the resistance. With a normal multimeter, you won't be able to detect the largest coil inside, which is the high voltage one that has these two ends, because you would need to measure in giga-ohms resistance. But to find the primary and the smaller feedbacks here, so we have more coils wrapped around in the same sense, you just measure the resistance across them, The larger value would be the primary, the smaller values would be the feedbacks. Now, to talk a little bit about the feedback coils that we have here, just like you saw, I have this button that I need to keep pressing in order to produce this high voltage spike from the secondary coil. So the next step would be to somehow automate this so that I don't need to keep pressing this button. And for that, I'm going to use a transistor. So I'm going to set up the transistor, and I'll be right back. Here I've set up the same circuit, the exact same circuit that you saw previously, only I replaced the button with a transistor so that it will carry out the switching operation automatically. But in this case of a transistor, we need something that will trigger it. So we have a couple of options. We can either add a button with a voltage source and a resistor and connect it to here, and press the button, and that will trigger the transistor and will do the same thing that you saw in the previous example. We can add another coil, so we can take another piece of wire, wrap it around the core of the flyback transformer, and that will create a small feedback wire. It doesn't have to be with as many wrappings as the primary. We just need a small voltage to trigger it. But so that I can play around with the frequency of the triggering, I'm going to connect a 555 timer to it. And here I have my 555 timer, and it also has a small 7805 to provide a 5 volt voltage source. Just gonna set it up here. Once again, I'm gonna use 12 volts. I don't have a good power supply, and I can't run this thing for a long time. But here we have the output pin of the 555 timer. I'm gonna connect it to the base of the transistor. If you're wondering, it's an IR-LZ44, which is the one that I had that could handle the currents of this. So I got this set up, and just so that I don't burn out the transistor, I'm also going to connect I'm also going to set up a small heatsink for it. Okay, so I'm back after setting everything up. I got my transistor here, which I've replaced the button with, and I've added a diode that prevents the current from going from the source to the drain. Also, I've added a capacitor, a 1 kilovolt capacitor between the source and the drain. To trigger the transistor, I'm using a 555 timer. I've added a pot to the timer so that I can play around with the frequency. This is just a voltage regulator from 12 to 5 volts so that I don't burn out the timer. And let's see how it works now. So I'm gonna turn it on. I'm just gonna turn the lights here off so that you can see the spark better. But here you can see it, and I can play around with the frequency. And you saw a nice demonstration. Burnt the wire here a little bit. That's because we're changing the frequency and the duty cycle, and that causes more triggering here or less triggering. Some points that I forgot to mention through this video. There is an importance on the direction that you wind the coil, the primary coil. You want to always wind it clockwise. So if you begin from here, let's say, and you're looking at the coil like this from the top, I hope that you can see it. You want to always wind it like so. If you're connecting your coil and nothing happens, the first thing you need to do is check for just the conductivity to see that everything, not conductivity, but check for shorts to see that both wires are properly connected, and if not, try to switch them, and then it should work. Another very important thing is that this is high voltage, so never touch this in the way that it works right now, because you will get electrocuted and it's not nice. When you're done playing around with it, always take the negative end of the flyback transformer and just touch the positive end, and that will discharge any remaining voltage that is inside, and you will actually hear a small click of the discharge. If you want to find the negative for the flyback transformer, which is something that I noticed from comments that many people have difficulties with, you can just set this whole thing up just like I did here, and then you take the positive end of the transformer, and the pin that it will create a spark with, that is basically the ground of it. This is also how I found it, because you can't measure the resistance of the larger high voltage coil with just a normal multimeter. You need to measure in giga-ohms, and that is not a function in a normal multimeter. So that's it. I hope that I covered everything that I wanted to explain. I had a whole idea in my mind, but when I push the play button on the camera, everything just gets mixed up. So that's it. I hope you like this explanation. If you like my videos, please consider subscribing, and thank you for watching, and I'll see you next time.